Morning, everyone. Sorry for being late. 1 minute. I was just trying to get the right app opened up. So we are getting closer to the end of the semesters. I hope you're ready. And I just want to make a quick announcement about the final exams. So I checked with a calendar. The final exam is scheduled on the Friday, which is supposed to be on the 14th of Friday. Okay. And by the cylinder, the registrar office is a syllabus that was scheduled from 7:30 to 9:30 a.m. That is a little bit um, how to say too early for some of the students, and so I decided to push it to the afternoon. But then again, I heard that we may have other exams scheduled in the afternoon of Friday. So I'm proposing right now from 2 p.m. to 5 p.m. All right, let me say this again: 2 p.m. to 5 p.m. on the Friday afternoon, 14th, May the 14th, Friday, 2 p.m. to 5 p.m. Now, if that doesn't work for you, email me or text me, or send from a chat message. I will check that once the course is done, and we can reorganize the time. All right. But can I get a suggestion from you guys right now? Does that sound like a plan, like 2 to 5
Yeah,
p.m. on Friday? Okay.
yeah,
Get a
that
yes.
works.
Okay. Anybody else? Good.
Is that going to be online like the other tests?
Yeah, exactly. It's gonna be same format as before. Excuse me. Yeah. So it's gonna be we upload the problem and you fill up yourself and upload it. Okay. All right. All right. So if we're all happy with it for now, let me just put it temporarily from 2 to 5 p.m. on Friday, May the 14th. Okay. All right. Again, if you have any other inconveniences, other things you want to do that conflict with the exam time, email me. We can work it out between ourselves. But keep in mind that if you cannot sync with the time, I have to redesign an exam for you every time when student requested. So that is going to be a lot of work for me. So I want to make sure that we do that properly. Okay. All right. So that is that. The second thing is on the course design, the lab design lab. I get more interesting email flooding in yesterday talking about the design lab. Very happy to see that, first of all. Second of all is that you are welcome to use any creative ideas, but on the concrete strengths, we are limited within 8 KSI, 8 KSI concrete. And I'll modify this on the slides, but that's the cap. We cannot go beyond AKSI. Anything below AKSI is free, free game, right? Whatever you can do with that, that's fine. Okay.
Recording in progress.
And the other thing that I want to talk about is the steel. So grade 75, 75 KSI grade steel is the cap for the reinforcement. Okay. Anything you design below grade 75 is fine. But again, you have to follow ASTM standard, right? So you don't really want to go um, with like say 440, 55, some odd numbers, right? It has to be the number that we commonly use. For example, 60, 75, these are the two numbers we commonly use. I suggest we adhere to that unless you have special thoughts, like special design that require a strange reinforcement. Okay. Now, last but not least, um, it's up to 4 team members, so you're free to join up with whoever you find working the best, but it doesn't have to be 4 members, right? You can even form your own 1 member team and do it all yourself. Okay. And I had experience before from previous semesters. One student sent me a design that I found awfully familiar. And I opened up his design or her design and found a similar design online. Okay. And that just say that do not copy design from online. Okay. Because I gave you a simple problem, so you should be able to find a optimum section. The point of this exercise is to help you to do your senior design later. And also when you go to the design office, when the senior engineer asks you to check on the member strengths from the computer design, you are able to do that with a very efficient way. Okay. I can give you a joke maybe. Um, I got my first consulting job once I graduated from my master's and went to the design office. and nobody says anything to me because they're just trying to see what I can do. So one of the senior engineers threw me a very thick binder of the existing design and also a bunch of the files. And I spent like without saying anything, just say, Bob, take a look at this, right? So I spent the whole morning trying to figure out what's what. And in the afternoon, I started filling in the Excel sheet on the computer, and that's when they feel like we can probably take on the assistant job. So I personally benefits a lot from this uh, so-called mini design, and I feel like this is a very good way for you to just kind of have a feeling of how design is usually done. But in reality, in the design office, you just need to build this process of your own process once. I actually use both ways, although there's a MathCAD where we can program equations, and there's also MATLAB and Excel sheet. So I have both Excel sheets and MathCAD program sheet for me to do design. Once I develop that, I be able to crank out maybe like say a few hundred beam designs in the design office every day. So that is very efficient. Okay. So I hope this process will help you. So try to really walk through, and don't mind if you come up with a so-called section is a little bit ugly, means it's just conventional, nothing fancy. That's fine. That's not the fancy we're looking after. It is the smallest section. Okay, smallest section give you the large capacity, give you the sufficient capacity in this sense is the best. Okay, so as much as you can reduce the section in the concrete, that's the best. All right. Again, we'll have sufficient time. Next week is the final week, meaning last week of class. We will go through some review process next week, and won't be any homework next week. I will leave all the homework this week, so you have time to work on your design and homework and review for the lectures. All right. Okay. Let me continue on with the column, and I'll circle back and answer all your questions. So please try to save your question at the end of the lecture today, okay? Because I just really want to cover the column design section today, okay? All right, thank you, and let me share my screen. Um, here we go, okay. Oops. Oh, okay, all right. So lecture 27. This is one of the last lectures on column design, but this is very important. Okay, but before we start it, I want to quickly go over what we talked about last time, right? So column, right? We talk about column, and columns in terms of compression, isn't it? It's always in compression. But when we have eccentricity, which most likely we'll see in the real scenario, we have bending moments. We have bending moments. So in that scenario, we're talking about a PM interaction diagram. PM interaction diagram. Okay, so what is that? Is a force axial load in the y-axis and a moment in the x-axis, and we're trying to draw an envelope. Right? So what does this envelope look like? Right? It looks like a bear belly, like I said before. It looks like a bear belly. So it goes linearly up to a peak, right? Go over the button and then go back and intersect on the x-axis right here, right? So this is the envelope. And before I start saying anything, the definition of this envelope is that outside is bad. Outside the envelope is bad. On the envelope or inside the envelope is safe or good. Okay. Okay, so that is the definition of this envelope. So this is called design. This is also called column design envelope. Oops. Column design envelope. Okay, and if you really want to see one of these printed out in nice format, you can take a look at the appendix or textbook if you have it. Okay, if you don't matter, right? Early next week on Monday, I'll show you some of the typical design envelope chart looks like, and maybe walk through a little bit how you utilize that for design. Okay, but this is actually the design envelope. Okay, and last lecture we talked about there are several critical points. There are critical point A, where there's almost no eccentricity, pure axial load. The axial force is going throughout the section, right? And then goes along, we have a pure compression, meaning like zero tension section, zero tension point, zero tension point. Okay, that means the entire section will see compression, no tension. Okay, as we travel along this and see the button where is the peak. Be careful when I say the peak, I mean it is peak in the axis sense. Okay, is the maximum bending moment you'll find, and this is actually where we call the balanced failure. Balanced failure. What do I mean by balance, right? Meaning that the steel yields, right? Steel yield, okay? Or you can call it a yielding point, right? And this is when we have the tensile reinforcement yielded. And then you go on and traverse a little bit more along the line, and you came across a point D here, where the strain in the steel has reached the tension limit, and 0.005 tension limit. And we call this tension controlled case, right? So that is the point D, okay? And keep going till you hit the x-axis where we call this point E, and this is when eccentricity equal to infinity. That means the sections subjecting mainly bending moment, almost no axial force, almost no axial force. Okay, some of you may ask, how does this happen, right? How axial force can be zero? I just couldn't imagine that. Well, you think of it, axial force P is consisted by the compression of the concrete, compression of the steel, minus the tension of the steel, minus the tension of the steel. Is that right? So when that happens, the compression equal to tension, when this case happens, P equal to zero, right? So you can immediately think of this. What we have seen this before. What this is a bending of beam, bending of a beam subjecting a pure bending moment, right? And if you remember in the flexure section, right, where we talk about compression equal to tension, C equal to T, and there's a JD, right? So when the extreme case, for the extreme case, when the eccentricity equal to infinity, the column converted into a bending beam, bending beam. All right. So this is what all these points are about. All these points about, and we also walk you through a little bit why we have these points, or why chronologically we have these points. Sorry, my English haven't spoken for a long time, isolating at home. Anyway, so what happens is that under the stress state, okay, or strain state, and I think that let's be more explicit, saying that strain state is better. Strain state, okay? So talk about the strain on the cross section, right? In the cross section. So for case A, we say that it's purely uniformly compressed, right? Uniformly compressed, also compressive, right? So this is the strain distribution, right? Matter of fact, let me rotate that so it's just more vertical. Well, sorry about that. Let me redraw it. Okay, you don't have to. You can keep them horizontal, but it just for me it's easier. So in compressive, let me think. What we need to do is let's do this way, compressive. Okay. So this is the pure axial loading, right? Pure axial loading. That is the strain. And for case B, what happens is that we start rotating the plane. Excuse me. Started rotating the plane. So you see this triangle shape. You see this triangle shape. And this is so-called the zero tension, right? Zero tension. Okay, zero tension. And then you go on and you rotate the plane a little bit more, rotate the plane a little bit more, and you start to see tension now. And at the level of steel, epsilon s here equal to the yield strain epsilon y here. So this is the balanced failure. Balanced failure. And you keep rotating till you see that the strain in the steel elongated, right, increases, and then increased to a limit. We call it a tension control limit 0.05. So this is tension controlled. And at the end, right, at the end, you keep going to an excessive state that at E, the compression all of a sudden equal to tension, equal to tension, and this is so-called pure bending. Pure bending. Okay, all right. So as you can see that this is the strain state. All right. So what about the stress? What about stress? Okay, now this is where things are a little bit complicated. Why? Now in compression, concrete is good. So able to take all the compression without failure. Able to take all the compression without failure. So the strain and stress distribution profile looks same. But as you increase the strain in the concrete, right, and here still fine because it's still in compression, but it's just this triangle distribution, right? Triangle, trapezoid, or triangle distribution, not trapezoidal yet. And then as you start to see balance failure, the stress stays different. Stress stays different. Why is that? Think about what we start doing here is use Whitney stress block, right? Use Whitney stress block. To simplify the calculation, so the compression becomes a block, okay? And we say that this is 0.85 F prime C, remember? And this is beta 1 C, okay? Beta 1 C. And for the tension side, since the steel yielded here in terms of stress, this is Fy, okay? In terms of stress, this is Fy. What happens to the concrete? The concrete simply cracked, does not bear any stress anymore, does not bear any stress anymore. And you keep increasing, right? So supposedly for the next step, things stay the same. The concrete compressor zone, although stay the same, okay, stay the same. Why is the same, Bob? Because the steel started to yield, but when the steel yielded, it does not change one bit of the tensile forces. Why? Because the reinforcement here still experiences a yield strength of Fy. Yield strength of Fy. Now the compressor zone might change slightly, but will not change significantly. Will not change significantly. That's why we went through the iteration of flexure design. Remember, we went through the iteration of flexure design, and then just keep increasing, right? And at the end of it, you start to have this nice. Let me just use C to represent compression. Nice two-sided story, and this is Fy, but this is total tension force, and C equal to T, and eccentricity equal to infinity. Okay, so these are all the strain and stress states for the column. These are all the stress and strain for the column. All right. Okay, so we said all about this. We said all about these, right? So what is the calculations entails, right? What exactly we're trying to do with this, right? So I will walk you through an example, but you will see that essentially for the column design, for exam, for homeworks, for later in the design office, all we are looking after is to construct this P&M curve, PMM interaction diagram, and B, find out the ultimate capacity for P and M given the cross section, All right. Okay. So now let's begin, right? Let's begin the journey, right? It's very interesting, very interesting. Question? Anything? Okay. All right. So example, right? Example. Uh, given the column section below, oops, section below, determine the following, right? Determine the following, right? So what is the section? Section looks like this, a rectangular section nicely showing up here, okay? And I say, you know, this is a 4 number 9 bars as a flexure reinforcement, very typical, okay? So 4 number 9 bars. And I have a stirrups surrounding it. So let me use a hooked stirrups. Now, when you see the stirrups, you may notice that this is slightly different than the stirrups I show in the previous beam designs. Okay, beam designs. Why? Okay, look, let me just put here in beams, right? For the reinforcement configuration, what you normally see is that this is up direction and the reinforcement, the stirrups is going like this, has a bend at the bottom here and then has a hook, right? Now here, there's no connection between them. And why is that? Because this is not a regular stirrups, okay? This is also called tie. The reason why we have this continuous hoop is that These will provide the tensile stresses when the column is subject to compression, the concrete inside trying to bust, and this tie will confine the concrete, all right? So if you are experienced designer, actually now you are because you have taken this course, you go out there, you see this type of reinforcement, and this is beam, immediately you can see this is beam. If you see this type of reinforcement, it's either a column or beam. Most likely it's going to be a column. Okay, most likely it's going to be a column. All right. Okay, so that is the section. That is the section. Now the height of the section H, equal to a 20-inch, and the width of the section equal to a 12-inch. Okay, 12-inch. Now the top concrete cover, that means the edge of the concrete to the center line of the compressive reinforcement here is so-called D prime, and that is 2.5 inch. D prime, 2.5 inch. And now for the conveniences, it's almost symmetric, and you see this a lot for the column. This side is also 2.5 inch. This side is also 2.5 inch. Okay, all right. So that is that. That is that. Now, at this point, you look at the section, right? This is all is given. You start to think about it, right? And you start to wonder, like, which side or which direction is the axial force pointing? Is the axial force pointing, isn't it? All right. So before you start anything, right? Let's call this x-axis. Okay, let's call it x-axis. Why is that? Because this is what we call normally the strong axis. Strong axis. Why is that? Why x-axis is a strong axis? Now, in mechanics materials class, right? Mechanics materials class, briefly, we talked about it, right? The moment inertia I equal to 1 over 12 BH cube. BH cube. So the bigger H is, the bigger moment of inertia is. So when I have an axis that is parallel to the shortest distance of the section, which means it's parallel to the width, that gives me the strong axis, means it gives me the maximum moment of inertia, right? So corresponding to the y-axis, y-axis is called the weak axis. Weak axis. Okay. All right. So that is the terminology. So where is the y-axis? Y-axis right here in the middle and goes along this direction. Okay. So we have a strong axis. You have a weak axis. All right. Now, normally when we determine the PM diagram, we have to tell you which axis this is with respect to, right? So here, let me state it clearly. It is with respect to the strong axis. Strong axis. All right, strong axis. Okay. Now, in the exam or in the daily scenario, if you were not told which axis that this is referring to, you better do both axes. You better do both axes. Okay. It sounds a little bit more work, but it's actually not. If you have the Excel sheet built like in design lab setting, it just plug in the number differently, right? It just plug in the number differently. But anyway, we are talking about with strong axis. That means my axial force, okay? I'm just clear this up so easier for me. You don't have to. You can keep up there. I just don't have the room here. So that means the axial force is either going to be on the top or on the bottom. In this case, I am assuming the axial force is on the top. I'm assuming the axial force is on the top. Of course, it's going to line up with this y line here, but this is actually with respect to x-axis. So you were confused again, right? So why, Bob? Why is along the y-axis when you're talking about this is with respect to the strong, which is x-axis? That is, if I want to talk, this is with respect axis, meaning I will have moment with respect to x-axis. Okay, that is the definition of with respect to, with respect to. All right, and one more caveat. So now you see this symbol here, is a cross mark, right? It has a meaning that this is the end of the arrowhead, right? This is the end of arrowhead, meaning the axial force P is acting towards inside of this paper here, towards inside of this plane here. Okay, so if you see a dot like this, that means that's the arrowhead. That's not the arrow end, right? If this is arrowhead, meaning the force, axial force is pointing out towards outside of the plane, outside the paper. Okay, just a little bit clarification. All right, so now I know that my axial force is going this way, so I'm going to see a axial force and also the bending moment. So the question is, one question is one. I want us to determine the axial force P and bending moment M corresponding to the balance failure. Corresponding to the balanced failure. Ooh, sorry, one more thing. Balanced failure. Okay, balanced failure. So immediately in your head you say, ah, that is point C. Okay, so in my head quickly I'll draw the drawings, a bear belly, and that's the button right here, isn't it? That's the button right here. Okay, you're trying to ask me point C, that gotcha, right? Not too bad. All right. Second, we're trying to determine P and M corresponding to a tension failure region. Tension failure region. Oh, Bob, why are you doing this? Right? Why are you speaking jargon again? What do you mean by tension failure region? I don't want to even think about it. Well, think about it. It's not that bad, isn't it? So on this diagram, okay, always have this mini diagram in your head already. Think about it. This is point A, this is point B, this is point C, and point D is between C and point E, right? And now to get clear, C is where the balance failure happens, right? D is where the tension controlled happens, right? D is where tension controlled happens. So before I do anything, I will draw a line cross O point 0, 0, right, to D. And this shaded region is what? Tensile failure region, okay? Tensile failure region. So Bob, you didn't tell me that before. Well, I did. In terms of phi, this is what? This is 0.9. This is 0.9. Okay. In case you forgot, right? In case you forgot, you think about what we said last time before. If I draw another line from O to C, and this region here is called the transition. Okay, it's called the transition. So phi is a function of the strain, and last layer of steel, and that is epsilon T. In this case, we have one layer reinforcement, so same as epsilon s, but that's fine. Now the last but not least is, we use a different color here, is this region here, and this, ladies and gentlemen, is the compressive failure. Okay, this is the compressive failure. You may say, ah, Bob, this is easy. During the day of the exam, I'm just gonna have my lectures note ready. When you say this, I'm gonna go back and take a look at it. Well, it takes about a minute for me to remember this mini diagram. Okay, so to pull out from my hard drive of brain, takes like less than 30 seconds. So it's best that as a simple diagram, you can remember this. So it will save you a lot of time on the job site. Okay, it will save you a lot of time on the job site. All right, so that is a PM corresponding to tension failure. So I just identified a zone. So what do you mean by that, right? It means that we want you to find a point, any arbitrary point, right, between point what? Between, this is what, sorry, this is tensile, right? Tension failure region, or tensile failure region, right? Between D and E. Okay, between D and E. All right. Okay. Now number 3. Keep going. We want you to find P and M for a point for a point in compressive failure region. In compressive failure region. Okay. Now, from the mini diagram, this is clear. You're trying to find a point from A to B. Oh, actually, let me put it here, A to C. Okay, A to C. All right, and then you go on. You say number 4, PM for a pure axial load case. PM for an axial load case. What is that, right? That means my eccentricity E equal to 0, right? And this is essentially point A. All right, point A. Okay. And don't forget that the concrete property and the steel property is given, right? The concrete and the steel property are given, and that is the concrete F prime C, concrete F prime C is 4 KSI, 4 KSI, and the yield strength is 60 KSI. 60 KSI, my favorite numbers, my favorite numbers. Okay, all right. All right, well, that is our problem. That is our problem. So where to start? Where to start? So when you're trying to solve this in the exam, right? You don't know where to start, of course. You panic, you think, this is complicated. I better take a look at the lecture notes, right? So here, without doing anything, start drawing the diagram, strain diagram, right? Strain diagram. That means I have my reinforcement here, that is for number 9. And then I start drawing my strain, and the strain looks like this, and it has a compressive failure here, epsilon Cu equal to 0.003, always, right? And on all these curves, right? On these curves, every point, it has to have a compressive strain of concrete reaching 0.003, right? And then you extend the line, and you say here, I have a compressive strain for the steel, epsilon S prime, and I have an actual compressive zone distance C. I have a tensile reinforcement here, epsilon S. Okay, so this is a strain diagram. This is a strain diagram. Okay, now continue on. The internal stresses look like what? Internal stress looks like a concrete Whitney stress block, compressive, and this width is 0.85 F prime C, and then this fellow here is beta 1 C equal to A, which is the effective compressive zone. You know this before. And at the level of steel, right? Level of steel, the force is AS prime multiplied by FS prime. Be careful, this FS prime in the stress in the compressive reinforcement. Okay. On the tension side, it has a tensile stress from the steel at the bottom here, so AS FS. Okay, this is internal forces or stress distribution, so I call it stress distribution. Okay, so internal forces, just to simplify that, I have compression from the steel, which is CS prime, compression from the concrete, CC, and I have a tension from the reinforcement, which is TS. So that is the diagram. Okay. Needless to say, if you have this drawn out, just copy it directly from the lecture notes. Even if you don't know anything for a problem 10 points, this is worth 2 points. Right? This is worth 2 points. So if you run out of time, you don't know what to do, draw this, get 20%. All right, fair and square. All right, so now before I do that, I say, you know what, I'm gonna recall the curve introduced previously. That is the P, this is M. Okay, so the curve looks like this. Oops, my drawing is shaky. All right, let me redraw it. Okay, a better button right here. So this is A and B and C and D and E. Okay, so this is where the curve's at. And I'm trying to find points, right? Take a look at the question, right? What are the points? I need to find point C. I need to find somewhere between D and E and C and A. So I need to find A. So clear this out, put a color here, A. You can write beside it, and C, okay? And somewhere between D and E, and somewhere between A and C, okay? So all these are something we need to find out. Okay. All right. So let's begin. Right. So number one, first problem, we want to find a point C. So how do I find point C? How do I find out point C? So what is point C? Point C is so-called a balanced failure, isn't it? Balanced failure. So it gives us the hint, right? What is balanced failure entails, right? It says that from the strain diagram, which I draw here, from the strain diagram, which I draw there, I know that at the balance failure, the reinforcement epsilon s here, tensile reinforcement, has reached the yield strain of what? 0.00207. Remember that number, okay? And also remember this number is for grade 60 only. It changes if it's for grade 675, right? So I have a compressive zone C right here, and I have a compressive steel epsilon S prime here, which I don't know, But I do know that concrete at the top here have a 0.003 of compressive strain, all right? Another definition is the depth of the reinforcement right here, D, is known, right? We'll find out that. Okay, and then this is the strain diagram. All right. Okay, so now the question is, what is D, right? D equal to H minus concrete cover right here is C, C. So H is, what is H? Let me see here. 20 inches and minus a 2.5. So 17.5 inch. Conveniently got, right? Conveniently got. Very simple. Now, C, which is a compressive zone, equal to what? Equal to the triangle here, right? So it is epsilon Cu, like we did for Fletcher, divided by epsilon Cu plus epsilon S, right? And then multiply by D. Now, epsilon Cu equal to 0.003, and here 0.003 plus epsilon S is 0.00207, right? And D, which is the depth, now 17.5 inch. 17.5 inch. My point has become a slash, sorry. 17.5 inch. So now this number arrives at 10.3 inch. Not bad, not bad. That is C. Okay. Now with that, I start computing A, which is beta 1 C, because I want to get to the stress diagram. That is 0.85 multiplied by 10.3 inch, and it gives you an 8.76 inches. Give you 8.76 inches. Okay. Now, what is the stress in steel? Fs equal to the yield strength of the steel. Why? Because it just yielded, right? So that is 60 ksi, 60 ksi. Okay, 60 ksi. All right. How about the compressive stress? Right. Be careful. Compressive stress, you need to find the strain, right? So compressive stress equal to the Young's modulus of steel, ES, multiplied by the strain in the steel in the compressive region, epsilon S prime. Okay. Now you observe the strain for steel. Actually, you can compute that, and that is equal to C minus D prime, C minus D prime divided by C outside bracket and multiplied by a epsilon Cu. So this is epsilon S prime. So bring in the numbers. Fs prime, Es is what? 29,000 ksi, 29,000 ksi. Okay, multiplied by C minus D, right? What is C? 10.3 inches minus D prime 2.5 inches divided by 10.3 inches. The whole thing multiplied by 0.003, which is the strain in the compressive failure strain of the concrete. And now you got Fs prime equal to a 65.9 ksi. Okay, 65.9 ksi. All right, be careful. Be careful. Why is that? Because these numbers, right? 65.9 ksi. This has already exceeded the yield strength of the steel, which is 60 ksi. Okay, so that is not doable. Why is that? Because it cannot reach there, right? So you use Fs prime equal to Fy equal to 60 ksi. Kept it. Okay, kept it. Cannot go beyond that. Okay, and now you might jump out of your seat again if you're careful, right? If you're careful, you might jump out of the seat again. You say, Bob, you're saying nonsense now. Again, be careful, right? Because in the flexure, in the beam, you told us you will never allow the compressive reinforcement to yield in most cases, right? You will not allow the compressive reinforcement to yield for the beam, for the flexure design. Here, you does not only allow to yield, but also you kept it and you pretend nothing happened. You pretend nothing happened. How can you do that? Well, This is actually allowed in the code in column design or column design. Okay, in column design, you are allowed to have fs prime equal to fy, which means compressive reinforcement yielding. Okay, okay, you are allowed to have that. All right. Well, Bob, you're coding the code again, right? You just tell me about this allowed. Why is this allowed? Think of it, right? You think of it. What in the being is that we have compressive reinforcement mainly acting two purpose. One is to take care of some of the compression force from the concrete and to increase the ductility. Remember, increase the ductility. Second is that they acting as a hanger bar, right? There's no connection, right? There's no connection in terms of stirrups, so there's no confining effect. You think of it in the beam, if it yields, what will happen? What will happen is in earthquake, for example, in the Fukushima, in Japan, what happens is that when you have a compressive forces, right, the top bar was not confined. The top bar was not confined. So when they yielded, they start to deform significantly, and they what happens? They buckle, right? They buckle, and they change the deformation significantly. And what really happens at that is the concrete cracks. The concrete just gone. Nothing can hold it up together. So you see explosive failure when the compressive reinforcement yield in the beam. Okay, in the beam. So in the beam, yielding of compressive reinforcement is no, big no. Okay. Now you observe in the column things a little bit differently. Why is that? Because in the column we have this so-called ties. We call so-called ties. Ties are the stirrups that binding the reinforcement together, right? So since the column is designed to have or to bear compressive loading, right? To bear compression forces. So all these reinforcement, when they are trying to buckle, because these stirrups or these ties are confining them, right? I'm gonna use a different color here, okay? Oh, sorry, before that, let me use this. So what really happens is that these ties acting as a supporting point, supporting point. Okay, so the reinforcement will not buckle globally. That means the entire bar will not buckle out of the place. If it buckles, and will when it yield, it only buckles between stirrups, between these ties. Okay, between these ties. So naturally, if I provide more hoops, I can effectively avoid this scenario. As much as I can effectively avoid this scenario. So that means even if the bars compress to yield, they're not most likely buckle in the real scenario if I provide ties. See, so in a column this is allowed, but also this exemplifies the significance having closed end or closed or continuous stirrups, which means ties. Okay, so be careful. All right. Okay, so that is a little bit tips here. Anyway, so let's continue on. So I now find out the compressive stress of reinforcement equal to a 60 ksi yielding stress. Pretty happy about it. You know what? I have all the things I need. I start computing the internal forces, right? So Cc, which is the compression force from the concrete, will equal to 0.85 F prime C A B. Okay, and bring the number 0.85, multiplied by 4, multiply 8.76 inches, and multiply 12 inch, and this gives me 357 kips. And before I continue, I forgot to mention one thing. You see that when I kept my compressive reinforcement, and again, another difference between the beam and column is that in the scenario of a beam, you would go back and recompute your actual compressive zone, would you? Right? You have to rebalance your internal stresses to make sure that compression equal to tension force. But in column, you don't have to. In column, you find out the compressive stress in the steel and leave it as it is. Why is that? Because nobody requires you to achieve balances. Okay, that means the compression does not internal. Okay, when I say compression, is internal compression does not have to equal to the tension anymore. Okay, So this is the advantage. So be careful, okay? Now, compression from the concrete, just calculate out 357 kips. Now the compression from steel, CS prime equal to AS prime, okay? Fs prime, don't forget, minus 0.85 F prime C. For those of you who forgot where this minus thing coming from, go back to previous lecture, find out, okay? Now, 2-inch squared, why? 2, number 9 bars in compressive region multiplied by 60 KSI, freshly calculated out, right? Minus 0.85 multiplied by 4 KSI of a concrete. And this, ladies and gentlemen, yields at a 113.2 kips. Okay, now that is the compression from the steel. Okay, tension would equal to what? Tension equal to ASFY, ASFY equal to a 2-inch square, 2 number 9 multiplied by 60 KSI, and this gives me what? 120 kips, 120 kips. Okay, 120 kips. All right, so this is when the magic happens. I want to find out the axial forces, right? P, axial forces. And the previous equation show you P equal to CC plus CS prime minus TS. Okay. And then we also showed you that what is the moment? Moment should equal to what? Should equal to a CC multiplied by half H. Okay. And don't forget, this is with respect to center line. Okay. Not the neutral axis, but the center line. Okay. Just neutral, not neutral, just in the middle of the section. Okay. Half H is what it is for, minus half A and plus CS prime half H minus D prime. Okay. And minus or plus plus ATS and multiply D minus half H. Looking good, isn't it? Looking good. Why? Why? Again, Bob, right? Why? Why this negative sign here? Why this positive sign here? If I bother to ask, right? So this is why. You look at a column, right? Fairly complicated situation. And this is the column head, okay? And when I have an axial force, isn't it? And don't really like this, but anyway, now when we have axial force, remember this is x-axis, strong axis we're talking about, right? The force is somewhere here, okay? Somewhere here, along the line of y-y line, but somewhere here, okay? So what we're trying to do, or what we're have been doing, is on the section at the bottom here, okay? So the real internal forces as we drawn there is CC, CS prime, and tension goes the opposite sign, TS. All right, this is what it is. Okay, so XY, definitely we need a Z, right? So Z is here, Z axis is here, okay, throughout. So along the Z direction, what we're trying to do is summarize total force. So Fz equal to 0. And then you see that P, which is a minus sign, right? Plus positive sign Cc plus Cs prime and minus Ts equal to 0, right? So you put this to the right hand side, flip it, so you end up with P equal to Cc plus Cs prime minus Ts, right? And that is this equation right here. All right. Okay. Now we said we got to sum the moment, right? Sum the moment, and this moment is summarized is summed with respect to x-axis. Then that equal to 0. So external, internal has the balance, right? So external. This reminders bugging me. The external moment, right, on the left hand side. So x external. Okay, external equal to what? Now equal to the force P here multiplied by the distance between the force to the x direction. And this is so-called eccentricity, isn't it? PE, right? So this, ladies and gentlemen, is PE. Now the internal moment is what? Internal moment is, look, this is axial force CC from concrete, axial force CS prime from the steel. So these are bending in this direction, right? Bending in this direction. So they're also in the, well, they're actually in a different sign, right? So that is equal to a CC multiplied by half H minus half A plus CS prime half H minus D prime, right? So they are in the opposite sign. So I just put the number here, okay? So they balance PE, that's fine. Now, supposedly, right? Supposedly TS force is in the opposite direction, right? Is in the opposite direction with respect to CS prime and CC. But, right, the x-axis is dividing them, right? Axis is right here, dividing them. So you think of it, CC is going this direction. TS is also going to this bending moment wise, also going this direction. Okay, so they are in the actually same sign. They're in the same sign. So this is D minus FH. Okay, and that's why this is positive. All right, so you let external equal to internal, so you have a PE equal to this bunch. I'm just lazy, so forgive me if I don't rewrite it again. Okay, and now that equation, ladies and gentlemen, is the bending moment. Is the bending moment, total bending moment, right? So PE is the total bending moment equal to this bunch. So right here at the end of it, you write equal to a PE, right? Equal to PE. All right. Okay, a little bit mechanics materials for you. Okay, a little bit mechanics materials for you. All right. Okay, so now we have this cleared up. Let's just add things up, right? So let's take a look. Oh, sorry, I'm a little bit over time. Sorry about that. So we'll talk about how to plug the number in and get the P and M tomorrow, Thursday afternoon. All right. So let me promptly stop here. So sorry taking more time. If you have any question, please stay behind. And if not, I'll see you tomorrow, 1 o'clock. All right. Bye now. Thanks.
Professor.
Yeah.
When would you gonna have homework 7 and quiz 9 graded?
Promptly next week before the end of the last day for classes, May the 7th.
Okay, I just wanted to know. Thank
Yeah.
you.
We will also release all the grades before May the 7th, so you can do a self-evaluation. You know what I mean?
Okay.
Yeah.
Thank you.
Yeah, not a problem.
Have a nice day.
Yeah, you too. Thanks. Anything else, folks? Anything else? Sorry for taking a little bit more time today. I'm a little bit carried away. Anything else? Oh, right. Okay. Catherine, Abigail, Tyler, Kyle. I'm gonna sign off because I'm a little bit late for the next meeting. If you have additional questions, email me. Okay. All right. Now, thank you and see you on Thursday, which is tomorrow. Okay. Bye now.